The Internet of Things, a network of physical devices.
Way back in 1999, a technologist named Kevin Ashton coined the term to describe a massive shift from a human-centric internet to a machine-centric one. But how does a system actually pull that off? Well, it uses what we call the knowledge hierarchy. It's a step-by-step framework. It all starts at the very bottom with raw data, basically just random environmental measurements from a completely dumb sensor. Next, you structure and filter that data so it becomes actual information. From there, algorithms go to work uncovering patterns, which turns that information into knowledge. And finally, at the very top, we hit intelligence. That's where the system uses the knowledge it gained to make decisions and control the physical world, totally on its own, without us humans getting in the way.
Moving right along to Section 2, Sensing the Physical World, where data is born.
To start that whole hierarchy we just talked about, we need hardware. We need the eyes and ears of the digital world. I mean, how does your smart AC actually know when it's time to turn on? It relies on sensors. And these sensors generate two fundamental types of data. On one side, you have analog data. These are continuous flowing signals representing things in the physical world, like temperature or air pressure. Now, because microcontrollers only understand zeros and ones, this analog data has to run through an analog to digital converter just to be understood. On the flip side, we have digital data. This is much simpler. These are discrete on and off signals, like a motion detector that just needs to know, is this room empty or is somebody in here?
Now, what's really interesting is how these sensors actually function. You don't just plug a sensor into a standard desktop computer. They run on incredibly lightweight embedded operating systems designed to run on almost zero power and minimal memory. For example, you've got Contiki, which is perfect for wireless mesh networking. Think of a grid of smart streetlights talking to each other. Then there's FreeRTOS, used for time-critical actions like motor controllers on drones, where a millisecond delay is a huge deal. Linux or Ubuntu Core provides robust security for heavy-duty industrial factory controllers. And Windows IoT is what's running behind the scenes on point-of-sale systems and your local ATMs. These OS variants are literally the tiny little brains driving our sensors.
All right, Section 3, the data pipeline, the plumbing of IoT.
Let's move to the next phase and see how this builds. We've generated our data out at the edge, but frankly, a temperature reading is totally useless if we can't move it to where it needs to go. Real-world data is messy, so engineers use what's called the ETL process to make it understandable for machines. First, we extract. We pull the raw data, usually in formats like JSON or CSV, using protocols like MQTT or HTTP. Second, we transform. This is absolutely crucial. This is the cleanup phase where we remove the noise, normalize units, like making sure everything is in Celsius instead of Fahrenheit, and we align all the timestamps perfectly. Finally, we load. We drop this beautifully processed, squeaky clean data into a storage database so it's locked, loaded, and ready for action.
And speaking of storage, you've probably heard the industry jargon, data lake. So what is it? A data lake is just a massive storage pool where both structured and totally unstructured raw data is just dumped, without any fixed format. Honestly, it sounds completely chaotic, right? But unlike a highly rigid, highly organized data warehouse, a data lake is amazing for long-term archiving. It allows artificial intelligence to dive in, swim around, and quickly pull out massive amounts of varied data for complex machine learning.
But to make true predictions, engineers have to blend different types of data together. Let's contrast dynamic data with static data. Dynamic data is your live pulse. It's real-time sensor readings, GPS coordinates, live telemetry. Static data is the contextual backbone, historical logs, equipment specs, past weather history. Let's say a building's energy use suddenly spikes. The dynamic data is what tells you it's happening right now. But the static data, like knowing a massive 500-person conference was scheduled in the auditorium today, is what actually explains why it's happening.
So where does all this heavy processing actually take place? There's a major architectural difference to grasp here. We all know cloud computing, those massive centralized data centers handling deep analytics and long-term storage. But IoT also heavily relies on something called fog computing. Fog computing brings the processing power closer to the edge, filtering data locally, right between the device and the cloud. Why? Well, imagine a power substation transformer is overheating. You simply cannot afford to wait for a warning signal to travel miles away to a cloud server, get processed, and travel all the way back. Fog computing can instantly analyze that data and shut down the transformer locally, stopping a disaster in its tracks. Which brings us to Section 4, Intelligence and Machine Learning, revealing the wizard. So we've collected the data, cleaned it, and stored it. Now for the magic. Except machine learning isn't magic at all. And this brilliantly illustrates that it is just highly structured logic given to machines by humans. Developers use scripting languages, primarily Python, to scrub and visualize these massive data streams. They lean on powerful libraries. For example, Pandas does the heavy lifting for data cleaning and transformation. NumPy steps in to handle complex numerical computations. And then libraries like Matplotlib and Seaborn are used to map out visual trends and graphs, taking raw, unreadable numbers and turning them into visual stories we can actually comprehend. Once that data is prepped and primed, we feed it into specific machine learning models to start making predictive decisions. Different models do different jobs. A regression model is perfect for trend prediction, like accurately forecasting tomorrow's temperature based on today's heat buildup. K-means clustering is used to group similar patterns together, which is exactly how you'd categorize the energy usage of different buildings across a giant college campus. And decision trees, they are incredibly good at classifying normal versus faulty device behavior. The machine basically learns what normal looks like and flags anything that breaks the pattern.
Moving into Section 5, Real-World IoT Applications, Making an Impact. Now that we actually understand the underlying pipeline, let's step out of the server room for a minute and look at how this solves real human challenges. The sheer adaptability of IoT is wild. We've got smart grids actively managing energy distribution to drastically cut waste. There's ambient assisted living, which relies on discrete sensors to help senior citizens live independently and safely in their own homes. In law enforcement, we're seeing specialized traffic cameras that can automatically detect illegal vehicle window tint levels as cars drive by. And in healthcare, advanced wearables are actively tracking users via EEG brain signal recordings, monitoring vital neurological health in real time. I want to pause here to highlight a deeply impactful use case that really puts things into perspective. IoT is currently offering unique, incredible personalization for children with autism spectrum disorders. By combining wearable environmental sensors with customized mobile apps, these systems can help track overwhelming stimuli, assist with daily skills, and help kids maintain their emotional balance. It's a beautiful reminder of exactly why this technology matters on a profoundly human level. Finally, let's look at Section 6, the future of IoT. What's next? We've seen what IoT can do today, but the connected world is evolving at lightning speed. Looking forward, one of the absolutely coolest concepts is the digital twin. This is exactly what it sounds like, a totally virtual replica of a physical system that constantly updates itself using live IoT data. So imagine a massive physical power plant. Using IoT sensors, engineers can create a flawless virtual simulation of that exact plant. They can run extreme weather simulations, monitor the pressure of every single virtual valve, and accurately predict a catastrophic failure in the digital twin long before it ever has a chance to happen in the real world.
So, the crucial point is, with billions of these devices tracking everything from our personal heart rates to our national power grids, strict governance isn't just a nice idea, it is an absolute requirement. We rely on heavy-hitting frameworks to keep us safe. You have ISO/IEC 3141 laying down a global reference architecture, while NIST sets the gold standard for risk management. Then there's the OWASP IoT Top 10, which guides developers on mitigating common vulnerabilities. And all of these enforce one huge principle: secure by design. That means security isn't some patch you download later, it is built into the very DNA of the device from day one to protect our privacy and our safety.
Which leaves us with one final, incredibly provocative question to think about. As we rush to build a world of 27 billion connected sensors, as machines quietly learn our every pattern, our habits, and our vital signs, who actually governs the intelligence of things? It is the ultimate balancing act of our time, weighing incredible, life-saving innovation against the fundamental, unyielding need to secure our personal privacy. I really hope this explainer has given you a clear, structured look into the amazing pipeline driving the Internet of Things, and hopefully leaves you eager to dig even deeper into our connected world. Thanks for tuning in.